Check, check. And welcome, students. We are looking at Chapter 5 today. It's going to be on ratios, proportion, and percents. Involves fractions and decimals, and working our way through those. Our ratios and proportional relationships, these are studied in the 6th and 7th grade in detail, although even in elementary school you'll want to start using these phrases for students so that they will become accustomed to them. Anytime you can introduce something a little earlier, just ideas about them, it really helps solidify in their mind what's going on so it's not totally brand new and they see it. All of these topics we'll explore in this particular section. This is getting us into a little more complex mathematical theory. We're not just looking at one number, we're comparing numbers and using that comparison to I guess discover and explain certain things. So we're looking at in this first example, if we're just looking at 20 ounces, we know what that is. That's just one quantity. However, down below, when we're talking about 35 miles per gallon, what does that actually mean? Well, it actually means 35 miles for every 1 gallon that we go, and it's a little more abstract than saying I have 35 ounces or 35 people that I'm discussing. And this continues on with that same concept of looking at just plain whole numbers with one quantity and then changing it to the concept of a unit, which then leads into dimensional analysis. So now we're talking about units as centimeters and meters, seconds, we're talking about feet, inches, and knowing that we can't just add two numbers willy-nilly. They have to be within the same unit, and being able to go from one unit to another. Conversions are a big concept with our units. So this just carries that on a little bit further. Here is the definition of a ratio. Ratio can be written in a couple of different ways. We can write it with that, let me get my pen. We can write it in this format, or we can write really A line B, which is the same as this, just written horizontally or vertically. We can write it as any one of those formats. A rate means something where I'm comparing our two different units, and we say that two ratios are equal to each other just as fractions are if they are equivalent. But a ratio is not a fraction. So they're different, and we need to discover how it is that they're different as we're doing this. And we'll look at some examples that go through that. When I'm looking at, doing banking and I talk about the 28% rule, this is another example of applying my ratios to discovering whether or not I can get a loan or not. So let's look at this problem. In this particular problem, they're wanting you to compare the improvement rate. So they're going to want us to actually do that division just as in that banking problem. And this is one of your homework questions. So let's see how this is done and what it is that they're asking for. They want us to compare the white infant mortality rate. So you'll be looking at this column here, and we're wanting to compare the improvement rate. So it was 5.6 as compared to 10.7. And then since I want it as a rate, or just as in the banking problem previously, I'm going to want that as a percentage, so I'll multiply times 100. And for this one, let's see, when I punch this, I get 5.6 divided by 10.7 and multiplied by 100, and I get 52.33%. I believe they wanted you to round this to a whole number, so I would just write in 52% here. So that's what this would be, 52%. Similarly, they want the black infant mortality rate, so I just do similar, 13.8 divided by 22.7 multiplied by 100. And for that one, I get 13.8 divided by 2.7. I get about 61% because I had 60.8. So that's how I would work that problem. Let's look at our next one. In botany, we might look at a plant stem and how it grows, and we can find that depending on what the species is, it has a different ratio there. Pretty interesting. Here are my plants with that different ratios, and they talk to you about the numerators and the denominators are all Fibonacci numbers. They don't really tell you what those are. Maybe they discussed that earlier, but let's look at some Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13, 8, 13, 21, and so forth. And what those numbers are, 1 and 1 added together get me 2, 1 and 2 added together get me 3, 2 and 3 added together get me 5, and so forth. It continues on, and those are Fibonacci numbers when they follow that pattern. Here's another question that I've had some students ask me about because they're wondering what to do with something like this. It's very similar to the previous question, and in this one, since I'm looking at the 1900, you would do 2777000 divided by, let's see, where's the other one? For the 1900, it's 92 million. 92, tink, 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 tink. Get this number, and for us that number is, let's see, 2777000 divided by 92, 1, 2, 3, 1, 2, 3. I get this number here, 0.03018.5, really, and they want it per 1,000. So this is what our number is. So we go per 1,000 means 1, 2, 3, multiply it by 1,000, and you would say, let's see, moving that over, that'd be 30.2. I don't want to talk about 30.2 births. That just seems a little unreasonable. So I'll just write it as 30. Oh, I looked back to see what they wanted, and do you know that they do want me to say 30.2? They want me to round my answers to the nearest tenth, which there's what it said right there. I just can't imagine rounding a birth, but anyway, that's what you'll do. Same thing here. You would find that ratio and then multiply by 1,000. Similarly on the B part and those that follow, you take your number there, 1344520, and I'm comparing it to this other 1980 number, which is 227.123.123. I'll get this answer. When I get this answer, I will then multiply it by 100,000 because I want it per 100,000 people. So first I get what that ratio is, and 1344520 divided by 227.123.123, enter. And I get as this answer 0.059222996. They want it per 10,000 people, so I'll go multiply it by 100,000, sorry, 2, 3, 4, 5. So this answer is then, rounding it to one decimal place, 5922.3. All right. Oops, I think I copied that down wrong. I'm supposed to be, that's what I get for having messy writing. Oops, let me get my pen. I think it looks like, let's rewrite that, 592.3 should go in that box. Sorry about that. All right, just looking at it and double checking, and I went, whoops, that's not right. And similarly for the next one, you know, if you're having trouble, you can just email me. Many companies use rates to determine $7 for every 100 pounds shipped. That is reasonable. We use rates. Cooking, if you want to double your recipe, you've got to double everything, or vice versa. And then we talk about ratio of people. It's another way we use ratios in real life. Sports teams uses ratios, but their interpretation of ratios is not valid, so don't use that. So don't use this as your one of your examples, because they're not using ratios in the correct format, or they're not using it mathematically correct. They're not using their meaning for ratio is not the same mathematically, how if we put it like that. Airline rates, they aren't proportional just because of the nature of how it is that they make money. They don't make as much money on the shorter flights, so they have to charge more for those. And we'll look at ratio of people in a couple of different examples. So 1-to-1 is pretty easy ratio. But what that means, if you have 1-to-1 ratio, let's say we had 100 people, that would mean 50 of them would be women and 50 of them would be men. That would be a 1-to-1 ratio. And they would write it as, you could also write that as 50-to-50, but then that ratio reduces to 1-to-1. So we do reduce it like we do a fraction, but it doesn't mean exactly the same thing, because it doesn't mean 1/1, as a fraction would in a sense. If we look at ratio of males to females at a certain college, so for every 3 males there's 2 females. What that means is out of 5 people, then 3 of them would be males and 2 of them would be females. So that fraction would look like this if you wanted to write an equivalent fraction. For this one, I need 3 parts of water and 1 part of bleach. That makes a total of 4 parts, but that means that 3/4 of it is water and 1/4 of it is bleach. Looking at my rectangle here, the ratio of the width to the length. So if we say that this is the width, because we can turn it around and call it whichever way we want to, but if we say that this is the width and this is the length, and they'll always put whichever one they want first, written first. So that would be 6-to-9, but that can reduce because there's a 3 in each, and we reduce it to 2-to-3. This is not a ratio in a sense, although you could say that it was 25 miles for every 1 gallon, but it's not comparing the same quantity, so it's not exactly the same thing. So here they are explaining all of that in words, and so you can read through those as I talked about those. And there's our statement 4. No way to really talk about that. And ratios are like fractions, but they're different than fractions. We can reduce them like they're fractions, but notice a 3 and a 1 doesn't mean it's 1/3, or it doesn't mean it's 3/1. It means there's 3 parts of water, 1 part of bleach, and so that means there's a total of 4 parts. And so your fraction is 3/4 and 1/4 to make a whole. And of course our miles the gallon one is not really valid in this sort of sense. Unit pricing, which one costs more? This is comparing our dollars to $2.99 for every 36 ounces. And if you actually compute those numbers, so, and then I want to do $3.79 for 48 ounces. We'll see which one is the better buy. Put you on hold. And here I computed those, and I did find that the larger jug was the cheaper buy, but it's not necessarily the case. You do have to divide it out and see what you get. Just as in the miles to the gallon, you actually divide those numbers, and then you would have to write it's that many dollars per ounce. The next is the concept of dimensional analysis. This is looking at our problem and making sure that our units cancel. So I know that whatever the numbers are, you multiply everything in the numerator and divide by everything that's in the denominator. These are just understood ones, so I wouldn't divide anything there, but if I perform this operation, what I would end up with is cents per hour. So I would get some number, and I think they're going to go through this with us, and they're looking at it pretty slowly. They're not just canceling out here like I would have done, but they kind of move these over very, very slowly, and they show you how you end up with cents per hour. And then you would do your computation with our numbers, which were 0.3 over 7.85, and they did that computation and they ended up with that many cents per hour. Of course, and this is dimensional analysis, and I would definitely get students looking at this. It's a very difficult concept, especially when you're looking at physics and chemistry problems and your science problems. They will have to convert units. Even in the 7th grade, they're going to be converting from miles per hour to miles per second or feet per second, or converting from days to years. Very, very useful tool, plus it's a lot of fun. All right, if you have any questions, be sure and email me. Thank you.